Hi everyone, and welcome to this session with Chris Penny from Siemens. He is going to talk about running CFD on your rocket in minutes using pre-built rocket simulation. And I'm going to pass you over now to Chris.
Hi guys. So my name is Chris Penny. I work in the Siemens academic program. I primarily oversee the student competition teams. So obviously the Spaceport competition is definitely one of those. So I have actually a background in CFD. I come from a smaller company called CD Adapco that was acquired into Siemens. And that flagship product for that company was Star CCM Plus. So back in that day, I used to run part of tech support, or not run, I was part of tech support. And I supported about 40 different companies during that time, which was a lot of fun. So part of that being aerospace companies. So a little bit of background on why I kind of created this. I've noticed a lot of the rocketry teams, they want to get into CFD. Platforms like OpenRocket are fantastic, but they like to run CFD so that they can fit in things like drag at different altitudes into the software, and then make better predictions as far as like how that rocket's going to perform. I've seen other teams too also want to understand, like, if they're putting pressure taps on the surface of the rocket, what does that pressure distribution actually look like? Or if you're doing cooling channels inside your rocket nozzle, what's that temperature profile look like? So these are all questions that can actually be answered by this rocket simulation. Teams need all that information, but they also don't have time to spend on building these simulations by hand, learning the software, learning the interface, and then also learning the subject matter. What type of mesh model do you use? Where do you add the mesh refinements? What type of boundary conditions do you use? What type of turbulence model do you use? And that goes on and on and on. So this is a very easy way to use a pre-built simulation, feed your CAD into it, mesh and run it, and it really just takes a few minutes to do. So with that being said, I will go ahead and share my screen. Okay, and get one of the things set up real quick. Okay, so this is, if you go into our community site, there's actually a link to the simulation that I'm showing you here. And what you can do is you can import your geometry into this and start working off of it. So there is some pre-built geometry in this, and that is fed into the simulation process so that if you're going in and making changes in the future, if you want to change the size of your fins, or if you just simply want to make different boundary condition type changes like atmospheric changes or pressure changes to your chamber and things like that, it's very easy to iterate on that. But either way, so I'll go ahead and start. First, I'll come up here and go to 3D Cad Models, and you can see there's 3D Cad Model 1. So I'll right click on this and edit. And in here, you can see this geometry. So there's this kind of wedge shape, right? And then if I zoom in down here, you can see this, there's this rocket, right? And by the way, the mouse controls, left click is kind of rotating about a single point on the screen. Right click is pan. The middle mouse is scroll in and out. So I can kind of come in like this, and you can see like the rocket on the inside, right? So you can see this fin here, and then the base, and then here's the actual nozzle. So this is basically this surface here will have a high pressure and a high temperature, and that will push actually a different gaseous phase into this. And so that will actually be its own separate phase, where this out here is actually going to be pushing in air into the domain. So the first thing, just after kind of looking at this, is the first step that I would suggest is to change the number of fins in this parameter down here. So if you have 3 fins on your rocket, 4, 5, however many you have, I would put this number in down here. For us, it's 4. And so there's nothing to particularly change. As the next step, I will come in and actually import my geometry that I'm going to be working on. So, so I'll go up to this, right-click, import 3D CAD model. And in this, I actually have the Purdue rocketry team, their geometry in this. And so I have this. You can import different file formats. You can see that there's a very long list of different import options. Normally, I would just recommend like a parasolid file. Usually that comes in cleanest, and it's a very common file format that you can use. So so X_B or X_T. And then I'm going to hit open. And so now you can see this rocket. Now, obviously, this rocket is not positioned how I want it to be positioned in, because what I want to do is I want to take the CAD that's built into this and then mirror this so that it reflects this geometry. Now, I'm specifically doing that because this CAD is already fed into the entire simulation setup. So like I said, it's very easy to go back and change this CAD. Whereas if I import geometry every single time, it's going to take, you can do that, but it just takes a lot more time to do. So the first thing then we're going to do is rotate this. So I'll select this, this, and this. So this is my geometry in this. Oh, and by the way, actually, before I rotate this, I would highly recommend only importing really the bare necessities for this CAD. If you import the entire geometry, it's going to operate a lot slower, right? So for this, I just have the external surfaces because, you know, that's obviously the most important. And then even the fence here, I've even excluded some of the geometry here for the base, some of the nuts and bolts, just because it's not really needed. I even excluded, you know, all the internals, even the base here. The base in reality kind of extends from this surface over to here for this nozzle. But yeah, so I'm just working off of what you see here on the screen. So anyways, so I'll control click this, and this, right click, transform, and rotate. And initially, I just want to get it pointed in the same direction as this rocket is. So you can see the tip is over here, the tip is this way, so that's good. So I'll hit OK. Next, I'm going to translate this down to kind of sit, well, ideally sit right on top of this, right? So I'll control click this, and this, right click, transform, translate. Now, in order to figure out how much to move it, you know, I could just keep iterating on these numbers, but a much faster way of doing that is to come up here and use this ruler icon. So to do that, just so I can see this a bit better, you can see it's kind of in this transparency view, which makes it hard to kind of move around and see. So I'm going to turn that off. And now I can see, you know, this rocket. And what I want to do is I want to match kind of this area here, maybe like this lip in here, to the back end of this, right? So let me go ahead and do that. I'll use the ruler icon to try to figure out how much that movement needs to be. So I'll click here once, zoom out using my middle mouse button. Oops, I accidentally clicked off of it, it looks like. Click once. Okay, zoom out. Then I'll put my mouse pointer over this, zoom in. It's still there, okay. And I want to position it right about there. Okay, now you can see in the output window, I have dx, dy, dz. So that shows me how much that distance was in all three of the axes. So I have a more precise, you know, more precise values that I iterated on just a little bit. So I'm just going to put those in. So I'll put this, and all right, perfect. So you can kind of see it sits right on top of that geometry that I have, the pre-existing one. So I'll hit OK. And now the other thing that I need to do is to move this so that the fins for this sit in the same location as the fin that I have in my CAD. So just as a side note, to do this a little bit easier, there are hotkeys. So like if I hit T, That's the top view. F is front, S is side, right? So I want to get a front view. Now, this doesn't really help me too much because I can't get directly head on to this geometry. You can see now kind of left to it, now I'm kind of to the right of it. So to change that, I'm going to come up here, go to projection mode and parallel, and now I'm always directly top down on it. Now I can't quite see how the fin lies on it, so I'm going to go back and go to transparent, and now I can see that fin, right? So now I'm going to hit Control and click these again, and I'll right click, transform, rotate. And obviously it's rotating about the wrong axis. It's rotating about Z, and we don't want that. We want it to rotate about X here. So I'll set that to 0 and this to 1. Okay, so that looks pretty good. Now I just have to get the angle rotation right. Now, again, I iterated on this beforehand. So it's negative, what was that, 36? Yeah, negative 36.8. And now this geometry, here's where it was, here's where it is. And I can see that pre-existing CAD right here in the background, right? So even the tip right here is kind of sticking out. Okay, so it's in the right location now. So I'll hit OK, and that is all set and ready to go. Let's see. Now, the thing that I need to do next is move the operations that I've used to get this in its location up in a different part of the tree. And the reason why I'm doing this is because I'll need to go in and modify the sketch, and I want the sketch to sit on top of the imported CAD. However, the imported CAD is happening after I made that sketch. So if I go in and edit the sketch right now, and I can just kind of show you this real quick. And if I come in and edit this sketch, I don't know how much to move this, right? Because there's no geometry behind it. So what I'm going to do is I'm going to take import, rotate, move, and rotate these all and move them up here, up right above domain and body sketch. Actually, I have to do these one at a time. So I'll come up here. Okay. Actually, I'll make this window a little bit bigger so it's easier to do it. Rotate body, move body, and rotate body. Okay, and I'll just hit update because this all is asking for it to be updated. Okay, so we're good to go. So now when I go in and edit it, now I have my geometry here. However, now I'm running into a different issue. Now I'm not seeing through this geometry. So I can either go back to transparency, but it's honestly a bit busy for my taste. So what I'm going to do is I'm going to cut open this geometry that we have here, this geometry here, that is. So to do that, I'm going to go over to scene plot and go to clip planes. And you can do clip plane 5 or 6. 6 is more oriented in our view. So I'll enable this. And now I can see this kind of geometry on the inside. If you want a little bit more definition here, because it might be a little bit hard to see, I can turn on the mesh, which is just, in this case, it's just the tessellated geometry from the CAD. So I'll turn that on just to visually see it a bit better. And now I will go back to, actually, sorry, before I do that, it's best to click off of this. There we go. Click off of the clip planes, because then if I accidentally start clicking on that clip plane that was shown in this view, because like if I clip it, you can see, or click it, you can see this little red outline. Then it'll start moving around the origin of that. I don't want that. So anyways, okay, now I can actually start going in and modifying this. So let me do that. So here, you can see that there are some constraints in here, like there's this anchor constraint, and I want this to move down. So I'm just going to delete that, and I'll move that down. Then I'll move this up, and I'll anchor that in place. So I just right click on it. Okay, that looks good. I'll anchor that too. Okay, move some of these other points. Okay, I don't want that to move. I'll anchor that too. This is just my own personal preference. I'm just trying to make sure that this stuff isn't moving around. Now it looks like there might be a little bit of a taper to this, so I'm going to remove that constraint that it's horizontal. So I'll fix that, come back out. The rest of this looks pretty good, except that you can see that the rocket is starting to kind of converge right in here, right? And this is another reason that it's good to have that tessellation on. I can turn it off and it's kind of hard to see. If I turn it on, I can see geometrically it's starting to change there. So what I'm going to do, I'm going to move the nose point down here, move this here, right? But now, here, let me turn this off so you can see better. You can see that this tangent point is kind of out of whack, right? So I can see that it's actually pointing off in this direction by this little round handle. It's a little bit hard to click, so I'm going to click back on the spline and try to grab it. There we go. Okay. Whoops. I don't know why it's doing that. Seeming to click, kind of lock itself back into that. There we go. Okay, I got it that time. Okay, so now I'm just going to mess with this and this to get it to be the right shape. Or whoops. Okay, now if I hit undo, I can get that to come back. And let me pull this, anchor it. Okay, there. Now I'm just on this point now. Right click this, fix it. And then I'll move this. So it's not an exact match, but it's really close. Okay. So that looks pretty good. Okay, let me go back and work on the nozzle a bit. So I'm going to move this up just a little bit. Actually, I'll keep it like this just to give it enough room. I don't want to put the boundary condition right next to a convergent part of the nozzle, because then the flow is just going to immediately run into something. So I'd like to give it just a bit of room before it actually hits that converging section. But this looks pretty close, except this throat is obviously not quite right. So what I can do here, let's see. Well, first off, I probably want this to be about like this. Okay. Now, this may not exactly match your nozzle. So what you can do is you can actually mess with the surfaces a bit. Like if I click this and delete it, I can start kind of messing around with this so that I get it set the way I want it to be set. So in other words, like if I, delete this, I can kind of just start deleting some of this stuff, and I can start moving this around, and that's perfectly fine to do. So what I'll do here is I'll set a fixation constraint. And you don't want to do this for too much of the geometry, because it's, well, you'll see here in a moment that I'll have to rename a few of the surfaces. So that's good like that. Okay, and I'm going to turn on this tessellation. Okay, I can see it kind of stops. Whoops. Go back to the last view. Move this to be down here. Fix that, and then I'm just going to use a spline just because I don't want to mess with like a kind of a circular curve. And this almost looks flat, but put it there, there, and there. Okay, so fine tune this. Okay, so that looks pretty good. So I'll hit OK on this now because everything kind of matches for this CAD. And so now we have this updated geometry. Now, The reason why I was saying I don't want you to delete too many surfaces is because what you'll notice here is that nozzle is now just this CAD, right? It used to be all of this, but now not so much. Well, between nozzle and nozzle 2, that is. So what I'll need to do is make sure that this geometry in here is actually associated to the surface it's supposed to be connected to. So what I can do is click this, and I think it was this one, and I can right click this, rename nozzle 2. So this will get dropped into this surface. Okay, so now if I click nozzle 2, is it the full thing? And it looks like it is. Okay, so between nozzle and nozzle 2, okay. Now it's important to name this the same because these surfaces that are being produced from this, again, are fed into the entire simulation. So you just want to make sure that it's being fed into whatever's there already. So you're not having to do any sort of rework. Okay, so that's good. I think the last thing to really change here is the fin itself. So let's see. Just make sure I'm not missing anything. Sorry, 1 second. Okay, yeah, so the first thing that I'm going to do is come down here to fin 2 sketch, edit, and then I'll go to a perpendicular view. And then I'll just start moving around these points. And I want to try to get them to match as closely as possible. So that looks pretty good. Okay. Okay. So that matches that shape. And now I think the last thing that I need to do for the CAD before I can start running this is mess with the chamfers here. So what I'll do here, let me get back out of this parallel view so I can kind of see these edges a bit better. I'll come to the leading edge chamfer first and edit that. And then I want this to match the CAD that is imported. So let me turn off transparency. Okay, yeah, that's definitely a lot better. So the imported CAD is this yellow surface here. So this actually looks pretty close. Let me see. So if I hit OK on that. Okay, so it looks like it needs to be, well, actually this thickness needs to be a little bit thicker. So let me go to fin 2 extrude and edit that. Okay, so there's actually this handle here. So let me just drag that out a bit. And that looks pretty close. Okay, so if I go to transparency, you can see it's really, really close. Okay, now let me go back to fin 2 chamfer. Where's that at? Fin 2 leading edge chamfer. Okay, edit. Okay, so now this definitely needs to be edited quite a bit. So this needs to come back quite a bit. Oh, whoops. Okay, that looks pretty close. And then this, I think, is just not quite that much. Okay. Okay, so that looks pretty good. Okay, so we've got that, and then I just need to do this for the trailing edge. Fin 2 trailing edge. So I think actually I could probably use the ruler icon here to expedite this. So let me measure from here to here is how far? 0.0125. 0.0125. There we go. So that looks pretty good. And then this is just a tad bigger. Okay. All right. So it doesn't have to be exact, but I have it pretty close. All right, so now I think we're ready to move on. Okay, yeah, we are ready to move on. So I'll hit close CAD because our CAD is all set and ready to go. It's already transferred down to the parts level, so I'm not going to go through the tree. But the other thing to adjust before I start running this is the one would be the exhaust gas properties from the engine. So to get to that, I would go to Continua, Physics, Models, Multi-component gas, and then expand gas components, exhaust gas, and material properties. And so here you can see the dynamic viscosity, molecular weight, and specific heat. Now to get those quantities, there is a NASA chemical equilibrium code called CEA, which is chemical equilibrium with applications. For that, in that application, you can actually determine what those properties are for your engine. Now for the rest of the simulation, you can come down here to Tools, Parameters, and down here, you can change all of these parameters. So to change the free stream altitude, Mach, or temperature, you can change those quantities in here. And if you want to change the speed of your rocket, you really only want to change the free stream Mach because the free stream velocity parameter shown in this listing, so free stream velocity, you can see it is a function of whatever you set as free stream Mach. Now that is specifically set that way because it's used in the initial conditions. So just adjust this if you're setting the free stream Mach. And then you can also change the free stream temperature. In this instance is 300 Kelvin. You can also change this. So if you, I don't know, say if it's 50 degrees Fahrenheit, you can put in 50 F and it knows that F is Fahrenheit. So but I'll put this back to 300K. Now, if you want to change the chamber total pressure, that's here. Total temperature, that's in here as well. And then you can also change the altitude, and that will change the free stream gauge pressure along with the initial conditions. So once you're done with this, all you have to do is hit mesh, and then you wait for it to finish meshing. And then once it's done meshing, you hit run, and that's it. Now I have the run version of this here. So I'll go ahead and open this up. So this is what the mesh looks like. This is not what the initial mesh would look like. If you look very closely at this, you can see these kinds of bands of refinements behind it, right? These are part of the adaptive mesh refinement that's being used, where it will run, stop, look at density gradient, and if it hits a certain threshold, it will refine in that area and then continue the run, and it repeats that a few times. So that's what that is. Some of these refinements are set up to capture, things that we know we want to capture, like the exhaust. There are also prism layers to capture the boundary layer effects. You can see the fin here, but this is just the mesh on the surfaces. If I flip this around, you can see what the mesh looks like inside the nozzle. So again, you get these prism layers and some nice refinement in here. So that's what the mesh looks like. Now there's different layers that you can turn on and off in here. I won't go through that as much, but then I have my results seen in here as well. This has a lot of different layers to it on it that you can turn on and off. So right now I have CAD transparent and Mach turned on. You can see that they're colored. I can double click on them to turn them on and off. But if I zoom in here, you can see what the Mach looks like. If you don't like these little ISO lines, you can change this to smooth filled, or if you want to fill in a quantity for every cell, you can do that. So like if you can see this, like if I turn on the mesh, you can see it has a quantity in each cell, right? So you can kind of change the way that looks depending on your own tastes. So you can see that. You can kind of see some of this higher Mach in here. So So we have that. Let's look at some of these other ones. So there's density gradient. So just like the name suggests, this is where you're having a higher density gradient in your solution. I can turn that off and turn on 3D exhaust. So this is just looking at mass fraction of the exhaust gas if it's 0.5 or higher. So we have that. We have 3D of Mach. Now, I will say that as you change your run, you will probably need to change what this is grabbing onto. There's a threshold setup for a range of Mach values. What I did, so you can see that here, if I click 3D Mach, you can see it's being fed a part called Mach. And that, if I click it, you can see it's under derived parts. So if you go back to your simulation tree, where's that? Here it is. You can see that there's one for Mach, and then you can adjust the range of Mach values. So you can highlight or not highlight certain cells. So that's the only one that you really have to kind of modify a bit. There's pressure gradient. So you can see this is kind of set to just highlight some of the shock waves. Then you have streamlines, and I put in the name do not show while running because it has to, the way it's set up is it's set to update for every solve iteration. So you don't want it trying to compute the streamlines on top of the regular computations. It'll just slow it down if you have this up and you have the streamlines on. But you can click play up here and you can see the streamlines actually come through. So it's kind of neat. Turn that off. And then again, if you want to modify where the streamlines are coming from and propagating to and stuff, you could very easily populate this on the outside of the rocket. We have 3D temperature. We, if you want to look at the solid geometry, you have that. So I can turn off, this. That's kind of up to you. We have density. And these are on the symmetry boundary conditions. So keep in mind that any of the values that you're getting, it's going to be, in this case, we're having a 1/4 of the domain. So you'd have to multiply like drag and thrust and stuff times 4. So you have density gradient. And then exhaust, Mach, you already saw that one. This one is looking at the local pressure. The local pressure minus the atmospheric pressure. So where you get this little white line is where you can essentially look at for your nozzle if it's meeting a design condition, overexpanded, underexpanded. That's what that's really kind of intended for. You have pressure gradient. You also have pressure on the external surfaces, which looks a little bit weird because I have the solid geometry turned on. So if I turn that off, it looks a bit better. And then pressure vectors on external surfaces. So I probably want to turn back on the solid geometry for this, so it makes a bit more sense. So you can see where it's things are pushing out or pulling, and so like naturally here because you have this big boat tail, it's a big drag component, and you can see that from the vectors pointing all down in that direction. We have a Schlieren image, which is just really density gradient colored in a different way. Temperature, velocity magnitude, velocity vectors, and then you have wall shear stress. And again, actually it looks pretty good set like this, but this will help you kind of visualize like, flow separation and things of that nature. So that's pretty much it for the result scene. Then the other thing that I would recommend taking a look at is the plots. So like I can see how the cell count is changing across its refinements that it's making. You can look at the drag of all the external components split up or together, like in this one. You can look at the mass flow rate, and this is the x-axis here is all per solve iteration. It has to go through a certain number of solve iterations to find an answer that's not really changing anymore. You have residuals, which I won't really get into. You have the thrust. Again, this is going to change as its refinements are being made. And then you have these, which the X and Y have changed, right? So this is for the nozzle, and you're looking at absolute pressure in megapascals per the position in X on the nozzle surface, right? So you have that. Here you just have pressure set as a ratio, and then you have X position versus nozzle temperature, if you want to look at that. I think that is about it. The other thing that I'd mention is that while you're running this, and by the way, I think you probably saw it before, but I'll say it again, you'd hit mesh, you'd wait for it to finish meshing. It only takes a few minutes to finish meshing, but then you would run it. And what you'll notice during the run is that in the output window, you'll see it will initialize the solution. It'll go through an initial inviscid solution, and it'll use that as a starting point, and then it will actually start iterating. And during those iterations, you can open up some of these scenes and visually see how that solution is progressing. So you can see the shock waves start to form and everything. The runtime on, I'm doing this on a computer. I ran this for about 8 to 9 hours on one core. So as you add in cores on your computer, you can run this faster and faster. So if I ran it on 2 cores, it's going to run 2 times faster, 3 cores, 3 times faster, 4 cores, and so on. So I would definitely suggest doing that. If you want to do that, you can load the simulation like this. So file, load, I can come down here. And if I'm loading it up, if I'm using a server-based license where I'm checking out a license from, say, on campus, I can come up here, hit parallel and localhost, and I select however many cores are on my computer. And this is physical cores, not logical cores. So not like what you see with hyper-threading, how many actual cores you have on your machine. So on mine, I have 4, so I could go up to 4. I can't go beyond that. And then I would just hit OK. And then when I go to mesh and run it, it's going to run faster. Now, if you're doing this with POD, which is a cloud-based license where you're checking out the license from our servers, you'd come in here and select. Not seeing the button. Simulation. Is it server connection mode? Oh, here it is. License, you go to power on demand, you would put in your POD key here, and then you'd hit OK, and it would check out a license from our servers. But again, you would still go local parallel on localhost. You would just select this instead, hit OK. And outside of that, that's all I have. Actually, one other note, if you want to go in and make changes to your CAD, you would just come back up here, go to 3D Cad Models, edit this, and then again, you can just go in and start changing this. So if you want to change it from, I don't know, 4 fins to 3 fins, you can come in here and change the number of fins from 4 to 3, and then just update the CAD and then run the new simulation. Just hit close, mesh, and then run. Same thing as if you go in and change, I don't know, the shape of your nose here, you can come in and come up here to this, edit, and say if you want to make it a little bit shorter, right? So I would just come in here, delete that constraint, move it a bit, and then hit OK, close it, mesh, and then run. So it's very, very fast to make changes and explore a bunch of different configurations. Or like I said, change altitude, any of the conditions that you want to go and explore. So.
Ready for some questions, Chris?
Absolutely.
Okay, so the first one came from, and I'm going to really ruin your name, I apologize, Christoph. Are there any options to modify mesh manually, or is it unnecessary?
So yes, you can, absolutely. This is not a constrained simulation that you can't change anything in. Actually, let me show my desktop, just share screen. So all of the mesh settings are in here. So if I go to Continua, or sorry, not Continua, Operations, you have Automated Mesh, which is just a unstructured three-dimensional mesh. And then in here you can see, like, there's Surface Remesher, Trimmed, and Prism. And then you've got your default controls. So this is like the global sizing, but then you have custom controls. And so this is where we're refining like the boat tail and the, some of the other things that you've seen here. And then you have like volumetric controls, and that's like refining the exhaust area. So you can change any of those sizings manually. You can also change how much the adaptive mesh refinement is refining shock waves and things. So that's completely all open to your control. But the nice thing about this is it's baked directly in the simulation. So, you're not having to mesh and import it in. It's all directly here right in front of you. So
hopefully that answers your question. And the next one we've got here is, can you give us the link to download the software, please? Do you want to show us where they find that on your website?
I think the question you said was where they could find it, like where they could download it. Yeah. Here, let me make sure that I have that open. Okay, so let me start sharing my desktop. So if I just go to Google and type in Siemens Academic Guidance page, and then here it is right at the top. So I click that. This is, sorry, so that takes you to this. It's one of those first links. Either way, you want to get to this page. And this is really kind of your one-stop shop for everything. So this is like, for example, how to get our software. So if you want to get our software, you go into that and it explains, the process for going and getting a software grant. And that can include Star System Plus. Oftentimes rocketry teams are interested in things for like PCB design, for CAD software, for product data management, for composites manufacturing, planning, simulation. There's quite a bit that we can help rocketry teams with that I've not even really kind of gone into here. But that is how you can get that software. So take a look at that. But to get this file in particular, if I go under Learning and Student Competition Team Content and click that, there is a section for rocketry teams. So see, for automotive teams, and then for rocketry teams, this pre-built sim is used to, so this is the sim. So you click that. And then this will bring up the instructions and the sim file. So here's the sim file. So you can just download that. And then I've got the description here. Now, I will say that I'm planning to put this video tutorial up on YouTube, and then that will be linked in here as well. And the video, vice versa, in the description in the video, it will link back to this. So either direction, you should be able to find what you need. But it's got the description, all the instructions, quite a bit of information in here. So,
and again, in the chat I put earlier, you can speak to Chris tomorrow morning in the expo section before the live at 10 a.m. So between 9 and 10 CT tomorrow, you'll be able to go and find Chris and the Siemens team in the expo section. So do go find them tomorrow. The next question comes from Julian Chi. It says, I'm not too proficient in CFD softwares, but is there a way to iterate this through a range of free Steam Mac?
Yes.
Free Stream Mac even, sorry.
Yes. So all you need to do is come back down here to tools and parameters, like I was shown before. So if you have tools and then parameters, you can just come down here and change the free stream mock. Now, technically, you could automate that process, and I think that's maybe what you're asking about. On one hand, you could just run a bunch of simulations manually. You could queue up, 10 different simulations and run them, individually or simultaneously, kind of depending on your computer resources. That's one way of doing it. The other way of doing it, if you come up to the top, right click, and then you hit Create Design Manager Project. It'll take a few seconds for it to come up, but you can set up a automated process to go in and change that mock or other parameters that you have in there and test those, have it automatically run those conditions. And then you can also tell it all of the data you want from the simulation. So you can tell it like, yeah, I want the numerical data of drag, I want the numerical data of thrust, and those are just numbers it spits out. But then you can also say, I want to look at the plot of, the nozzle, nozzle pressure per position. You can say, I want to look at the result scene, and then just make sure that you turn on or off whatever you want beforehand. But you kind of just come through this and set that up to do that kind of thing.
So your next question is from Tucker Johnson. He says, why would you use less than the max amount of cores?
That's actually a good question. So I actually do that a lot because in CFD, well, I don't know necessarily for CFD, but I'll say for Star System Plus, when you use a core, it's not like other things where it'll use less than 100% of that core. It'll kind of do like it'll split up the load against across multiple cores. In Star System Plus, when you tell it to use one core, it's going to use 100% of that core 100% of the time. So if you are doing emails and other things and you want to keep doing that while you're running a simulation, oftentimes what I'll do is I'll use 3 of my 4 cores and leave that little bit of headspace so that I can keep doing the rest of what I need to do. If I'm running a sim at night, I'll close down everything off my computer and then I'll let it run on all of my cores and I just won't mess with it. You can still do stuff on your computer. It's just, it might be a little bit slower.
So your next question is from Abadiah, who says, can you elaborate more on meshing the strategy?
So I can, yeah, I'll take a stab at trying to explain that. Let's see. So if I open up mesh, so I have one boundary that's hidden here. So I'll right click, restore all hidden parts. So there's my wedge, right? So here, if I come up to my mesh settings, so you have a surface remesher, which is essentially just splitting up the geometry into more equilateral triangles. So here, I'll go to the remesh. So it's taking your CAD, which is this. I think it's this one. No. Yeah, geometry. That's what I was looking for. Okay, so you go from CAD, which is just infinitely refinable geometry, right? And then in the process, it goes from this to a remesh surface, which is you're just essentially taking these long stretched out triangles and making them look like this, right? So you get these equilateral triangles, and this is necessary before you actually get into meshing, volumetrically meshing the geometry. So this is using all of the mesh refinements that you are applying. It's just on the surfaces though. So in other words, like you can see how this is smaller. This is, much bigger out here. This surfacing in here is much smaller. And you'll see those same sorts of behaviors in the volume mesh because this is just I'm not going to get into detail here, but this is a pre-step that's needed to then go in and produce the volume mesh. So same here. So you can see all that small refinement. So anyways, after this, you have the actual volume mesh, right? So you can see that same sort of sizing. Okay. So I mentioned that because if I come back up here to the top, not this, you have the surface remesher. So the surface remesher is doing that kind of splitting up of the triangles. The trim cell mesher is these blocks out here. It's called trim cell grid because you're taking bigger blocks like this and trimming them down in size, right? It's halving them each time. So it halves them, and then, it gets small enough to where it actually can, hit all the refinements that you specify. The prism layer mesher is this. and that's refining or trying to capture really tight gradients. It could be heat transfer, it could be boundary layers, those sorts of things. So, and then in default controls, you have a base size. This is just a size that everything else references. And then you have some global sizing, like you want to try to target the surface size as being 100% of the base size. Its minimum surface size can get it down to 50% of that size. The number of prism layers here is 15. The stretching, so this is basically saying that each layer, so this layer from this to this one is 1.5 times thicker than this. So this is controlling how much that stretches out. There's max cell size. So that's controlling how big a cell can get. So these are hitting that max. So that's all the global sizing. And then you have these individual controls, like the base here is really, really small, right? Because there's a lot happening here in the flow. So I refine that. So like in controls, I can tell it what to refine. So in target and minimum size, I gave it a custom size. And in values, I gave it a target size, a minimum size. Also did a few other things, like I added a wake refinement. So I basically patterned this sizing out in this direction. So I won't go through all this. I know, we're somewhat limited on time, but I have different surface controls in here that control the meshing on the surface and around that surface. And then I have volumetric controls, which basically grab onto a full volume. So in like this case, for parts, I fed in the entire geometry here. And for this, I said, for the sizing, I want to try to restrain the size in the simulation in general to 1600% of the base size. Okay. The jet downstream, so within this arbitrary shape that I created, this cylinder, I want to refine it so that it's this size that you see here, right? So I can drive into this and you can see the value is 25% of the base size that I said earlier. Likewise for this, it's not quite as refined. I want to try to coarsen it out a little bit so the cell size isn't so big, because the more cells I have, the longer it takes to run. But I do want to try to capture that going downstream a bit further. So that's pretty much it for the mesh. I think the other one, I want to say this is in physics, is the adaptive mesh refinement. So if I come in here under physics, models, there's adaptive mesh. And in the settings in here, you can see it's a function of density. There's some functions in here, but I won't get into that. But that basically is setting the thresholds at which, if the density gradient is at a certain point, then certain point or higher, then it will cut down the cells and down to a certain level. But between everything I showed you, that's essentially the full mesh setup.
So you have got another mesh question here. It says, are there any methods for beginners to assess the quality of the mesh?
There is, absolutely. There's different ways of doing it. You can go and run diagnostics. And when you do that, it'll just kind of give you an output here. Honestly, I don't use that all too often. I'm usually more concerned about, like, if I go to run it and I'm running into problems with the problems where the residuals are either relatively high or I'm getting warnings in the output window, like turbulent kinetic energy is being limited or temperatures being limited, because there's limits for how high or low those values can go. Because if they're allowed to go beyond those ranges, the solution will blow up, right? But if I see it starting to be limited, and by the way, if you're running the simulation, you will see that at some point, but the number of cells that it's being reported for will start to go down over time, right? So, but if you see it going up, that's where you start to kind of wonder, okay, am I going to run into, a problem with it diverging? And if you do run into a problem, 9 times out of 10, I would say it's usually related to the mesh. And that's when you start to go in and kind of investigate. I will say for this simulation, you're not really ever going to run into something like that because just because of the geometry. The geometry is very, very simple in this case. But if you did, usually the first thing that I do is I go in and create a threshold. And then I'll look at cell skewness. And then I'll look at something like a range of values of 90 and upwards. Well, maybe 360 or something. I'll just go 400. No displayer, create, close. And now let me go find the threshold. Here it is. This will highlight visually any cells that have those problems, right? So in certain scenarios where I've had complex geometry or really like tight gaps to squeeze cells into, that's usually kind of where you find those highly skewed cells, and it'll highlight an area where you can go in and, you know, change the geometry, you know, eliminate maybe like little sliver cells that you have, or sliver like really like small gaps, or go in and refine the mesh so you don't have those problems. You can do the same sort of thing for like what I was mentioning. If you're hitting like a temperature limitation and temperatures are really, really high in some cells and those number of cells are growing, I come up here, I hit stop on the simulation, and then I'll make a threshold like this, but instead of skewness angle, I'll just do temperature. Like, and I'm just basically answering the question, where is that really high temperature? You know, I'll put temperature in here, and then I'll go in and, you know, here you can do a query, and that'll do min and max values. But I can say, okay, where's the temperature really high? So I could come in here. Yeah, let's see, 2500, let's do 2400. Okay, and then it'll show you, okay, that's where the temperature is really high. Well, in our case, it makes sense. But, you know, if you had it in an area where it's not supposed to be really high, it'll highlight like something that you can do to potentially fix that problem. Now, I will say this is a very, very shorthanded answer to this. There's a much more elaborate and probably professional way of doing this. But what I would recommend, once you get our software, we have what's called a support center, and it has all kinds of really good resources. Actually, let me pull that up real quick. So this is the support center. So I can come in here and hit Start System Plus, and then I can start searching for things. So I can look at cell quality, right? And then it will pull up all kinds of knowledge base articles and things that I can do. So like this, all this stuff that you see in here. And it will show you really good practical information about how to actually go in and explore these things.
That's a great answer. And I love the fact that you've already got this set up for help. You've got one more question here. It says, can the results be exported to an FEA solver for a fluid structure interaction simulation?
If you're going to do something like that, I would recommend doing that inside Star System Plus. Star System Plus does have finite element built into it. So that would be honestly the easiest way to do that. You can technically export. You can do an export of XYZ position and pressure and shear forces, and then you can map that on into a FEA package. And there's kind of a file export to import into FEA to do something like that. There are also other tools that we directly interface with that you can do kind of the one-to-one match. For something like this, you're not going to need to do a direct coupling so much. It's more of just a one-time export import to figure out like what kind of load you're seeing. You know, you wouldn't want to do like a flutter analysis or something like that on a fin, because it's very, very computationally demanding and complex to kind of just go into run, generally speaking. But I would honestly recommend just doing it directly within one software, because that'll just make it much, much easier to do.
I think that's time for everything. So again, I reiterate that Chris will be available to chat throughout this whole process. You can go to Expo on the left-hand side of the Excel Events main page and find Siemens in there. You can write directly to Chris, and he will be live tomorrow morning between 9 and 10 a.m. CT. So do go over there and ask questions to him directly. And thank you ever so much for everyone that's joined us today. We really appreciate you all, and good luck with the rest of the experience. We'll speak to you all soon. Do take care. Bye-bye.
Thanks, everyone.